is part of the project SecureROM. They investigate jailbreaks for iOS devices for the iPhone. iPhones are usually locked down and can't be rooted, as we call it, but technical users try to get root access from time to time anyway. There's a continuous cat and mouse game between Apple and people who find jailbreaks and Apple fixing them again. This jailbreak is a particular one because it's not fixable. QWERTY will introduce us to their work and explain what the problem is and what they found out. Please, warm round of applause for QWERTY.
Thank you. So today I will be speaking about the one weird trick that SecureROM hates. And this talk was already given at POC 2019 in occasion of the planned release of SecureROM. We had missed a deadline, but it is now available for download and free use at SecureROM.in. So I am Luca Tedesco, aka QWERTY. And you can find me idling on irc.cracksby.kim in the chat channel. On Twitter, you can find me at QWERTY or UIOPZ. I'm an independent security researcher with an iOS focus, and my main background is that I've been hacking iOS and I've been involved in the iOS hacking scene ever since I discovered iPhones a decade ago. However, today I am here on behalf of more than just me, because this talk would not be possible without the work that several people have put in place. I want to give a special shout out to Axiomax, which is the person who published the vulnerability that we were abusing, and also to Little Layla, who had it independently, and Sigudza for the exploitation strategies. And I also want to thank the entire SecureROM team, because we worked for months on end to get the infrastructure ready in order to turn such a powerful vulnerability into easy to use and reliable jailbreak for everyone. And the SecureROM team is composed of an all-stars group of iOS researchers. There's more than just these, but these are the main contributors. And the knowledge base of this group is pretty impressive. And it's possibly the best team that I've worked on in my entire lifetime. So I think it's really important to give them a shout out. And I'm very grateful for what we achieved and the work we put in. Thank you. So we'll start talking about what is SecureROM. SecureROM is the very first code that will run on your iPhone once you turn it on. And it's a stripped-down version of iBoot, which is the iOS bootloader. And this code is very important because it's placed into mask ROM while your phone is being manufactured. And it's basically the most trusted piece of code that can ever run on the application processor of your phone. The goal of SecureROM is to fetch an image from flash storage for the full bootloader, iBoot, load it in memory, and jump into it. So it's very simple, but it does a bunch of signature validation. And it also provides a recovery mechanism known as DFU, which allows you to recover a phone from an unbootable state or just do a complete restore of the device without relying on the bootloader to be sane. And you can actually enter this mode by pressing a special key combination while the phone is turning on. And I'm also going to mention Secure Boot a bunch during this talk. And iOS truly pioneered the concept of Secure Boot. It's one of the most long-running issues in the jailbreak community, the ability to load unsigned code. And it all starts from the root of trust in SecureROM. And every time you load an image in SecureROM, it will perform validation mechanisms, except on the original iPhone, where this was not the case for images that were already flashed into storage. And as I mentioned, yes, this is jailbreaking enemy number one, and jailbreaks want to bypass this. The DFU protocol is a fairly simple protocol implemented over USB control transfers. And again, the goal is to allow the device to get some data from the host. And since this is a stripped-down version of the bootloader, it's designed to be very simple. And basically, there is a special request that you can send to the device with some data appended to it. And once the transfer is done, you can do a sequence of other requests, which will tell the device to boot into the image that you uploaded. There's, however, other ways to exit DFU, including a special request called DFU abort, which will shut down the USB stack and reinitialize it from scratch. As I mentioned, this protocol is implemented over USB control transfers. And so I will go through what exactly a control transfer is. And basically, it's used to issue some commands from the host to the device. And you can actually send data with your request or ask the device to provide you with some data. Successful USB enumeration requires complying devices to support a minimum set of these control transfers. And each control transfer starts with a setup packet, which contains some information on the transfer that's about to happen. And so we have a request type, which specifies which direction the data has to go through. The B request, which is an index of what kind of request you're trying to do. And some other fields. But in our case here, the most interesting one is W length. Because if W length is set to be non-zero, the setup packet is going to be followed by a so-called data phase. During this data phase, the host will send data in a chunked fashion to the device. And again, as I mentioned earlier, this is the mechanism that allows your host to upload files to a DFU device. Although, if you specify a direction of in, the transfer will actually get data from the device. And again, the length of the maximum length of the transfer is specified in the W length field here. And when you send this data phase, the data that you want to transfer is going to be chunked into packets of sizes ranging from 0 bytes to 64 bytes, depending on what USB speed you're running on, and it will send it sequentially. Once the transfer is finished, a status phase follows. And in this status phase marks the end of the control transfer, and a 0-length packet is going to be sent. In the iBoot USB stack, a temporary buffer is allocated in order to get all these chunks, and the data gets mem-copied in the right place every time such a chunk is received by your device. USB and DFU work side to side, because as soon as you enter DFU, the USB stack gets turned on, and during the turn on, this temporary buffer is going to be allocated. And once the control transfer is issued, a pointer to this buffer is going to be copied in a global variable, and the USB stack will use this global variable to figure out where to put the data that it just got in memory. However, when you exit DFU, the USB stack is turned down, and the buffer will get freed. And so we get to the interesting part, which is our bug. So essentially, when we do free this buffer, the global variable of the destination of the data write is not actually nulled out. And these actually can cause use after free type of vulnerability. And so I'll recap the steps to get a trigger for this. So we will have to start a USB control request that has an associated data phase. And as the data phase is being sent out, we will interrupt sending packets and issue a new USB control request. In this case, we will issue a USB DFU abort, which will exit DFU, turning off the USB stack with it, and freeing the buffer. After DFU exits, it will try to load whatever data was loaded, but we don't send any legitimate valid data. And so DFU the image loading will fail, and DFU will re-enter. Once DFU is re-entered, the USB stack is available again to be used, but we have our dangling pointer still available. And if we send a data phase at this point in time without an associated setup packet, the pointer is going to be reused from the previous setup packet that we sent during the earlier DFU stage. And yeah, as soon as this happens, the data is going to be copied on top of such free pointer. And in order to accomplish this, we need some very good control over the USB stack. And so Little Layla and Sigudza's approach to this was to take an Arduino with a USB host shield in order to get complete control. And AxiomX's approach, on the other hand, was to coerce the USB stack in macOS to diverge from the specification and abort a transfer midway. And the second approach is not deterministic, but you can actually do multiple attempts, and many USB stacks will actually tell you how much data has been transferred once you abort a request. And from these, you can actually infer whether the attack was successful or not. So as much as it's not deterministic, we found that we got an implementation that could get very close to 100% reliability, practically. And this is a picture of the initial setup to test this out from Sigudza and Little Layla. However, there is a catch. If you actually attempt to follow these steps, nothing at all would happen, except for two specific devices, A8 and A9, used on the iPhone 6 and the iPhone 6s. And that's because on those two devices, there is actually a bug in the DFU abort functionality. Basically, the USB stack has its own task to process USB transfers, and Sigudza Layla noted that these two devices do not actually free the task once you tear down the USB stack. And so this structure is going to be leaked in the heap every time a DFU abort is done. And essentially, this gives us the primitive to overwrite the contents of our task structure. And once you yield from another task, from this task, the registers are going to be saved to this structure. And when you schedule this task off, the registers are going to be restored off of it. So the use after free write, in theory, would allow direct register control. However, this is not the case because the use after free write actually happens on the task structure of the currently executing task. And you can't actually overwrite the registers because those are live in the actual hardware-backed registers at that point in time. And when you schedule off, they will actually be saved back to the corrupted task structure, and so your corruption is going to be erased. However, tasks also have an internal linked list from which the actual next task to be scheduled is chosen. And so you can actually create a fake task structure somewhere else in memory, and with the use after free write primitive, corrupt this linked list instead. So the next time that the USB task yields back to the scheduler, it will branch into controlled pointers. And by doing this, we actually achieve direct code execution as the heap on the SecureROM is read-write execute. 32-bit ROMs cannot actually use this strategy, as well as A7, A10, A10X, and A11, which are the newer SoCs. There is no task structure leak to abuse in these, And no crash is triggered whatsoever, because the ROM is deterministic enough that every single time we exit DFU and re-enter DFU, the heap layout is going to look identical, and the buffer for the transfer is going to be reallocated at the same place every single time. And so we need to find a way to break out of this determinism in order to get a proper use after free scenario, where the write will actually hit something that's not supposed to be just generic data. And so AxiomX looked at the SecureROM heap implementation and realized that the heap will return the smallest possible hole available for a given allocation size. And so we can use this property to do heap feng shui. And essentially, what we really need is controlled allocation primitives. So when you actually send a USB transfer, there is actually an associated structure allocated on the heap. And you can actually have multiple USB transfers. In this case, they're transfers from the device to the host specifically, in flight at the same point in time. So for instance, if you request some data from the device is not actually going to be able to reply with that data if the host doesn't acknowledge that the data was received. And every time you send a setup packet in such a condition, while the host is knacking the transfer, it will end up staying around for a while. And this gives us the ability to call malloc and delay the free temporarily until the stall condition is cleared or the USB stack is shut down. But the issue here is that we need allocations to persist across a USB stack teardown and initialization in order for the heap shaping to influence the state of the heap when the buffer is going to be allocated next. And in order to pull this off, a state machine bug in the USB stack had to be abused. And this allowed us to have persistent allocations that will never actually get freed. And these, sorry. OK, so, and these actually relies on zero-length packets. So once you have a transfer from the device to your host, the structure will actually send up a zero-length packet once the request is fulfilled or the USB stack has to shut down. And the issue is that if you're actually shutting down the USB stack, the zero-length packet is going to be sent into the void, and it will never be managed because the pointer of the list of in-flight transfers is going to be nulled out later on. And this leak can be triggered conditionally because zero-length packets are actually only sent upon specific conditions. For instance, requests that are not a multiple of 64 bytes will not require a zero-length packet from the device. And so it's not actually going to be sent, and nothing will happen. So we can actually abuse this in order to carefully craft the state of the heap and end up with an exactly sized hole, which will be the preferred place for malloc to put the IO buffer next. And each USB request structure will also contain a pointer to a callback that is going to be invoked once the structure is freed. And we can actually reallocate a few of these in place of our old buffer. And once we perform our use after free write, we will be able to control this function pointer and get an indirect branch once we exit DFU next. And this strategy can be successfully used on A9X, A10, and A11, and A10X. On older devices, however, this technique is not actually usable, as every single transfer will end up leaking if the device has an in endpoint that's stalled. However, we can actually allocate repeatedly and have the heap almost run out, minus the size that we want to have for our next buffer. And this will end up creating a hole of the exact size at the very end of the heap, and that's going to be preferred by malloc. And so by using this, we achieve what's called checkmate. However, right now, all we have is code execution. And what we really want to have is a bootkit of sorts to continue boot normally rather than staying in SecureROM and DFU mode and jailbreak the device, hopefully. And so how do we develop a bootkit? Well, we do have code execution, and we are able to re-enter into the main function of SecureROM, which will attempt to boot the device off of flash again. And eventually, the bootloader is going to boot into the kernel. And once that happens, it will try to branch into its entry point. And so our goal then becomes to patch the kernel at the point in time at which the kernel is loaded in memory after it's been validated.